Because I have to be at your meeting.
Oh, okay.
So, thank you for time.
Yeah, it's an honor to have Christoph here from University of Michigan. And yeah, he will tell us something about exact results for Type IIB.
Okay, thank you. And thank you very much for the invitation. It's great to be back here. And what I want to do today is talk a bit about a somewhat broad picture on five-dimensional superconformal field theories at large N that emerged basically since the last time I was here. The title is Exact Results for 5D SCFTs with holographic tools from Type IIB. And before jumping all the way into it, I want to talk a little bit about observation practice, general scope of ideas. So the general goal is to better understand quantum field theory. I think we all know and appreciate that this is an extremely versatile and successful tool, which has lots of very precise and accurate predictions. But what we're lacking is sort of a systematic and analytic understanding of quantum field theory at the non-perturbative level. We know very well how to systematically do perturbative quantum field theory, how to catalog Lagrangians, and from those construct field theories. But beyond perturbative approaches, there are sort of lots of tools available, but not a systematic understanding. In particular, we don't even understand very well what the space of well-defined quantum field theories is. And that seems to be a somewhat substantial question, given that it is our go-to framework for each and every circumstance, at least on the slide here. So ranging from water to magnets and matter to particle physics, that's what we want to understand how to use it. So understanding the quantum field theory non-perturbatively, of course, is a tall order. One has to simplify the problem a little bit. And the laboratory sort of that I want to look at here is that of supersymmetric quantum field theories. So in a sense, making the curve a little more spherical. For supersymmetric theories, we have a lot of tools at our disposal and can actually get a little more leverage on quantitatively analyzing quantum field theories. And this is based on a combination of quantum field theory methods with various constructions from string theory. So on the quantum field theory side, supersymmetric theories typically have a whole moduli space of vacua, which one can analyze and study. I want to use supersymmetric dualities between supersymmetric field theories. And certainly not least, there's a tool called Supersymmetric Globalization, which allows to actually compute quantities whose form is not dictated by supersymmetry and strong coupling in quantum field theory. On the string theory side, this whole host of tools is sort of completed by using brain constructions to engineer quantum field theories in string theory, this way avoiding reference to Lagrangian. And there are, of course, the SCFT dualities, which tell us that string theory on certain asymptotically ADS backgrounds is equivalent to conformal field theories. And the combination of all these sort of alternative or orthogonal approaches, if you wish, have led to quite significant progress in the understanding of supersymmetric quantum fields. Now, the natural starting point, if I want to understand what is the space of well-defined quantum field theories, is to look at even more constrained theories. And the point here is that typically quantum field theories can be understood as a renormalization group flow between fixed points in the ultraviolet and the infrared. So if I want to map out the space of consistent theories, it's a good idea to start out by mapping out the space of consistent fixed point. And this, combined with supersymmetry, leads to superconformal field theories. And the first orders then is to catalog sort of the space of consistent superconformal field theories. And what I need to write down a superconformal field theory is certainly the superconformal algebra, which realizes the symmetries that I want to see there. And this problem has been classified. Suitable algebras have been classified a long time ago. In 6 dimensions, there are actually 2 possibilities, either 8 or 16 supercharges. In 5D, curiously, there's only one possibility, which has 8 Poincare supercharges. So there's only one choice for superalgebra if I want to realize the field theory. Then as I go lower in dimensions, there are lots of possibilities, which I stopped listing at some point. But the point is, beyond 6, there are no suitable superalgebras, and so this is the maximum number of dimensions in which I can realize.
You're simplifying, right? Like 60 and 40, those are infinite families. You just truncate for physics.
Yeah, by truncation. I want local quantum field theories.
In 5D, there's one, right?
There's one. That's right, this is the one, here, 4. Good, so this is sort of the first step to cataloging what's possible. And usually, of course, we're all down here in 4, 3, 2, and whatever dimensions are of interest for physical reasons. And one has to talk a little bit about why these higher dimensional ones, which are the ones that we're testing today, are actually quite interesting. And the way I want to argue for it is by just appealing to a precedent which made it all the way to pop culture. The idea is, let's assume for a second that we are, that string theory describes nature. We consider ourselves purely 10-dimensional persons. We write down consistent theories. And we find that there are 5 consistent theories, which, depending on the situation, sometimes one is a better description, sometimes the other. We find a fairly remarkable web of dualities, which sometimes appear somewhat miraculous. And we could be perfectly content and happy in 10 dimensions. But we would miss out big time if we wouldn't allow ourselves to also consider theories in 11 dimensions. And what I'm appealing to here, of course, is the sort of unified perspective that we get out of M theory, where by realizing the 10-dimensional theories as limits of an 11-dimensional theory, many of these miraculous relations can actually be understood in nice and geometric terms. So there is a good motivation to go beyond 10 dimensions in this case. And one of the perhaps most striking lessons that we have learned from string theory, that I believe is with us to stay regardless of whether string theory is realized in nature, is that a similar picture actually applies to non-gravitational local quantum field theories, at least to supersymmetric ones. And this claim is remarkable already at zeroth order. The reason is that it is notoriously difficult to even define quantum field theories, interacting quantum field theories, in dimensions greater than 4. If we come from a Lagrangian perspective, we will notice that it's just, there are no suitable renormalizable interactions to write down. For example, if I write down a gauge theory in dimensions beyond 4, and just do naive dimensional analysis, I'm going to find that the coupling constant has a negative mass dimension, and for that reason in perturbation theory, you get worse and worse divergences in each order. And the theory, at best, makes sense as a low-energy effective field theory, much like we think of Einstein-Hilbert gravity in 4D. And you would say that it needs some sort of UV completion to make sense. So it is, from that perspective, quite remarkable, the claim that there actually are interacting UV complete local quantum field theories in 5 and 6 dimensions.
You mean without including gravity?
Yes.
Still UV complete?
Yes.
Oh.
So this is quite, this is, if you come from a Lagrangian perspective, a very remarkable claim, but 20-something years of research into it have solidified the picture that precisely this is the claim.
But in the nutshell, if you were to tie it to string theory, will it, I mean, you might argue that it's related to open string, maybe.
Yeah.
But we know that open string alone doesn't make sense. Necessarily it requires open closed strings,
Yeah.
which means gravity. So how do you manage to avoid gravity?
Let me, maybe, can we hold off on it for just a
Sure.
little bit, and then
Sure.
we can come back to that.
Okay.
I think maybe part of it will be part of the story, so I don't want to go ahead too far. So the idea is, the claims that these theories exist, and they make sense. And they're actually, they not only exist and make sense, they're actually useful. And the point here is that the higher you go in dimensions, the further the theories are constrained. So in the list of superalgebras, which I had a few slides ago, there were a few entries in 5 and 6, and then there's a lot as you go down in dimensions. So if you want to make an analogy to this kind of stream, which I'm not sure, maybe somewhere not too far from here, the higher dimensional theories would correspond to sort of the upper part of the stream, where things are nice and orderly, they're constrained, and you actually have a shot at classifying. And then as you go down in dimensions, it's where sort of the stream broadens up, you have all sorts of substreams, and splits up, and becomes a little more fuzzy.
Is there a concept of quote-unquote swampland in this setting?
Yeah, that's a good question, which I'm sure currently, well, yeah, I'm not sure.
I suppose I'm not the first one to utter this word in this context, am I?
What are you saying? You're specifically looking for stuff that's not in this model?
I'm going to want something where I have a chance to actually compute some things. That will mean string theory constructions will play a big role from the get-go. You can ask, can you get away without using them? And I'll leave that as an open question.
Sure, but we're not going to claim that you generate all possible CFTs.
Yeah, I'm not claiming.
Right? 5 or 6. Okay.
I had the point here that a classification is within reach because they are so tightly constrained. But that always comes with a caveat. The classification usually has assumptions. And whatever your assumption is, you may have an easier or harder time to classify. And one should be open-minded about that.
So what is the status of the classification of the 1,0 theories? Because I thought that was included.
Yeah, if you think of the ones you can engineer in certain ways. That is my understanding.
And is it known whether there is even one that is not like that?
I don't think so. Okay, good. So the main point is that once one understands what's going on up here, one can flow down. In other words, if you have one well-defined theory in 5 or 6 dimensions, you can compactify it in many different ways and create a host of lower dimensional theories. And this perspective actually often gives you useful insights which you would not have gained by just staying in lower dimensions. For example, our poster child theory for the n equals 4 super-YAMLs has an S-duality symmetry, which appears somewhat miraculous if you look at it from a 4-dimensional perspective. But if you realize the theory by compactifying a 60 theory on the torus, then this S-duality are precisely the large diffeos on the torus. So just by embedding it, so to say, in a higher dimensional theory, you learned something, some new perspective on the property of this. You can be more ambitious and actually define new field theories in lower dimensions. A celebrated example are the so-called 40 class S theories, which you can get from classifying the 60 theories on punctured Riemann surfaces. These are isolated, strongly coupled quantum field theories in 4 dimensions, which you would have not seen if you were just sitting around playing with Lagrangians. So this is quite an interesting insight, and there are a lot more which one could go through, which I don't want to do here. As a somewhat amusing point, in theory space you can also flow up. There are lots of examples of 5D theories that actually flow to 6-dimensional superconformal field theories. So here you can also reverse it and study things else.
What's T7?
That's a name given to a particular theory, which I will discuss in more detail. It's a different perspective on the same 40 class theories. Okay, so the whole point this is supposed to make is that it's actually useful to understand theories in higher dimensions because they tell you stuff about lower dimensions, which you have a hard time getting directly in lower dimensions.
Are there efforts to venture into the 2D jungle in this way?
I won't go that far.
Do people go that far? A lot?
Yeah.
They do, I see.
Yeah, there are lots of relations between 2D theories and 4D theories and things like that. Okay, so this hopefully gave a little bit of an idea that this is hopefully an interesting thing to pursue. And what I want to focus on today is 5-dimensional theories. They have a big advantage compared to 60 theories, and that is they're closer still to Lagrangian field theories. So one can actually get some mileage out of conventional field theories. And what I want to do is, in the first part, I want to discuss how these theories are actually found and engineered, which hopefully will answer a little bit the question for why all this makes sense at all. Then I want to talk about the holographic perspective on these theories, talk about the SCFT dualities, and finally put together the field theory and string theory perspectives to get some quantitative insights into these theories, which, well, we will discuss a little bit and hopefully. Okay, so from 5D gauge theories to superconformal field theories is the first part. Just to reiterate, gauge theories, if I write them down in dimensions greater than 4, are non-renormalizable, and they at best make sense as a low-energy effective theory if you come from a Lagrangian perspective. But of course, this entire argument is based on a perturbative perspective. It's based on thinking of perturbative expansion, collecting divergencies, trying to renormalize perturbatively. And so the way out of this dilemma is that you may conjecture that the pathologies which you see in perturbation theory are really an artifact of not treating the theory properly. If you treat it non-perturbatively, it may flow to a strongly coupled fixed point. and this way be a well-defined theory. This is what Weinberg speculated as the asymptotic safety scenario for four-dimensional gravity. The claim is that for these gauge theories, it's actually, but it points to the limits in what you can do with perturbative Lagrangian analysis. And one has to sort of now wants to understand which gauge theories could potentially have UV fixed points. In other words, can I cook up, using Lagrangian methods, some necessary criteria for gauge theory to be well defined and flow to a strongly coupled UV. The natural thing you want to look at is the space of vacua of these theories. So being supersymmetric gauge theories, they typically have a whole space of vacua. At generic points, the conformal symmetry is spontaneously broken. So you trigger a flow from the UV CFT to some infrared dynamics, which you can understand in terms of the gauge theory description. And only at a particular point on this space of vacua do you find that there is actually, while mass scale is removed, so to say, and you get a strongly coupled CFT limit. And what you would formulate then as a criterion is that, well, if the gauge theory is supposed to make sense as a low energy effective description, then it should be a good description on all of the space of vacua where the conformal symmetry is broken. And if you don't find obvious pathologies, then you can hope that you can approach this point where you actually have the conformal symmetry restored in a smooth way and find a well-behaved theory there. This all can be made a little more precise, but this is sort of the general attitude behind this approach. And this program was initiated by Seiberg some 3 years ago. He looked at the simplest American gauge theory where this can actually be brought to fruition. And that's an Sc2 Gauge Theory, which has a Coulomb range, so a non-trivial modular space of vacua. And he found that so long as the number of flavors, the number of quarks in this theory, does not exceed 7, then indeed you find a well-behaved, low-energy effective theory on the entire Coulomb range. If you go beyond that, it blows up at points where it's not supposed to. But if you stay below 7 quarks, then the theory actually seems to be. And so then, the conjecture is that if this bound is respected, then you have a well-defined CFT as fixed point for this gauge.
What is locate means?
It means you have a positive, definite kinetic term for the gauge on the entire group. You want the convex pre-potential.
Same curve.
You want to go, yeah, you have, you want to look at it far below the rest. It's infrared free, so one with infrared dynamics. So there you go. It's infrared.
Is there some protected operator that shows you that since it's non-trivial, it must be interacting?
You can see it from just naive dimensional analysis of the coupling goes to infinity. There are lots of interesting things happening, which I will come to in a second.
Yeah, but everything can map out and choose out
well, I mean, you're looking at the limit where you're removing the mass. In the infra, what you described happens in the infrared. You freeze it. Okay, so this is a conjecture. We only looked at the low energy effective theory so far. The reason we believe it's actually true is that there's a string theory construction to back it up. So you can realize this particular gauge theory in type 1 prime string theory. I don't want to spend too much time on this particular construction. The idea is you can realize this as a theory on a D4 brane, which probes a D8-O8 combination. And in the string theory construction, you find precisely the same bound. You can realize the well-behaved theory so long as the number of flavors does not exceed 7. And in the string theory construction, you can realize the Coulomb range, and there's no obstruction to taking the limit where you approach the origin of the Coulomb range, where you find the strongly coupled conformal field. So since these two things line up so nicely, you actually have a case of saying there's something going on.
Roughly why an f is less than or equal to 7? How does that come about?
It comes about from where you place the D8 branes, and you have to make sure that on the entire interval, the dilaton does not go negative. So that you have
Previously, we were talking about using the sort of more unique higher dimensional theories, and then flowing up and down to study lower dimensional theories. Now you're asking questions about how do you know whether a lower dimensional theory has a higher dimensional origin that's well defined?
No, this is all horizontal in the space of dimensions. This is all 5D. I'm writing down 5-dimensional gauge theories, and I'm asking, does it make sense as a well-defined theory? Without talking about 6 or 4 or 3 or something, you can afterwards, once you have a well-defined theory, you can ask, how can I compactify it, and yada yada. But this is sort of the 0th step of saying there are actually good field theories.
And then what was the criterion for it to be good? You're answering Dan's question.
Yeah, the criterion is you want to have positive definite kinetic terms for the gauge theory.
Why is that not a weakly coupled concept?
It is a weakly coupled concept, but you're going. So the theory has a moduli space. You're going away from the conformal vacuum, so you're breaking conformal invariance. You can now go to the infrared limit, where you have a weakly coupled gauge theory. So this actually becomes applicable. And if on all of the Coulomb branch you have a well-defined effective IR dynamics, you would say at least nothing goes obviously wrong. So there may be a theory.
IR go to UV and then break down to some lower IR things, and everything has to be defined down here.
Basically.
And that defines okay.
Yeah, exactly. And of course, it's a little bit back and forth because I mean, with the field theory methods, you're confined to perturbative arguments, but you want to really push it further. And the way you push it further is by combining it with the string theory construction, which tells you, okay, everything you did actually made kind of sense because we're finding the same bounds. Okay, so now we have a field theory criterion which tells me which theories are potentially fine. And of course, if you did this thing for Sc2, you can now go and just do it for more complicated theories. And that was done shortly after by Trilliger and Morrison and Seiberg. And they classified the theories which have this fine IR dynamics on their entire vacuums. And what they found is several infinite families. I don't want to go through them in too great detail. You can have an SUN gauge theory. 5D, you can have a Chern-Simons term of the form F which A. And there's a bound between the number of flavors, the Chern-Simons level, and the number of colors. And so long as this is first respected, you do not find obvious conformations. In the same way, you can go through other gauge groups. As a cautious remark, in their analysis, actually, Curvature gauge theories very right away fail their criteria, but by now are understood to actually exist and make sense. And we'll come back to that later. So this is very much based in string theory considerations, which tell you that the criterion for having a well-defined effective field theory on the entire Coulomb branch is just too strong. We understand now it's sort of sufficient, but it is not necessary. So these theories make sense, but there may be more. And again, the reason why we believe that this list is actually not just conjecturally complete quantum field theories, but actually complete quantum field theories, is because we can engineer them in Type IIB string theory by using 5-brain constructions. So that's what I want to discuss a little bit next. How are these theories realized in string theory? And to that end, let me introduce 5-brain webs. So the idea is we have PQ5 brains in Type IIB string theory. They're labeled by a pair of charges. My conventions are 1, 0 is an E5, and 0, 1 is an NS5. And we want to look at an arrangement of these 6-dimensional objects in a way where all of them share 5 out of their 6 5 out of their 6 dimensions, and have the remaining dimension in a common plane, a 5-6 plane here. And you can cook up supersymmetric configurations of these brains if they are arranged at an angle which is dictated by their charge. So the horizontal one is 1, 0, vertical is 0, 1, and 1, 1 goes diagonal, for example. They can join and split so long as the charges are conserved and compact. So that's a simple set of rules for cooking up supersymmetric brain configurations. And what I'm giving here is this simple example of an Sc2 Gauge Theory, which I had talked about before. On this pair of V5 brains here, you have an Sc2 Gauge Theory. And the general scheme is that the length scales in the brain web actually correspond to mass parameters in the field. So in this brain web, we have 2 length scales. We have a horizontal separation of these NS5 brains and a vertical separation of these D5 brains. And what they correspond to in field theory terms is the horizontal separation corresponds to the gauge coupling, which is a dimensionful parameter in 5D. And the vertical separation of the D5 branes is a VEF of a scalar field which parameterizes the space of vacuum. So this is the Coulomb branch modulus. And in
These
the
angles are fixed by supersymmetry, I suppose, right?
Yes.
And how much do you have? How much SUSY do you have? 1/4, I suppose?
Yes.
Okay.
Yes. You get right. You get an enhancement when you look at the intersection of the near horizon limit. It's the usual. Sorry, I come back.
So the external legs are the flavor symmetries, or is that the flavor brain?
These guys are not flavor brains because I'll talk about flavors in a second. But yes, the external legs have something to do with the global symmetries. So now we have a realization for this Sc2 Gauge Theory, and we know how to dial the gauge coupling and the Coulomb branch modulus. So how to move around on the space of vacuum. And in the brain picture, there's no obstruction to just sending all the length scales to 0. And that's precisely what we would consider as the UV limit. In this limit, we get a very simple intersection here. It's a cross or X-shaped intersection. And the claim then is that this is the UV fixed point of this Sc2 Gauge Theory, which I just wrote down as a low energy effective theory. So on this intersection point, which is now truly a 5-dimensional locus, we have a superconformal field theory that's engineered by 5 branes, but it has a relevant deformation which flows back to this gauge theory description. And it's an infinite coupling. Yeah, so it's good. So with this sort of simple set of rules, we can now immediately engineer a whole host of theories. All you need to do is respect that charges are conserved in junctions of branes and that they are aligned in the proper way. So an immediate generalization which I can tell you is you can just add more D5 branes here. Remember the horizontal ones are D5 branes. So here we have 3, and that engineers an SU3 gauge theory. In this case, one without transients. You can also add flavors. Those correspond to these semi-infinite D5 branes sticking out here. In that case, you get fundamental strings connecting the gauge D5 branes with these external D5 branes, and those are the flavors. In this case, it's SU2 in 2 flavors. So also,
So all these constructions are supposed to give us CFTs in
Yes.
what dimension now?
5.
But I thought you were after a parent theory in 5. Now you're having a whole
Sorry,
zoo
this
of
wasn't
5D.
clear. My
CFTs.
motivation was we're interested in theories up to 4 dimensions. That's where we live, as far as we can tell for now. So I want to look at these higher dimensional theories to learn something about theories in 4 and below. And higher being 5.
Yeah, but in 5, to what degree do you have some kind of control or uniqueness? Do you have a large class of CFTs?
That's what I'm trying to get at.
Okay.
What I'm having here is a toolbox which allows you to engineer a whole lot of theories.
Infinitely many possibilities.
Infinitely many theories.
In 5D.
In 5D.
Okay.
Because all you need to do is tie up these branes in a way which complies with the supersymmetry rules, and for each of those you get a CFT.
I want to ask a really terribly sub-question. So, I mean, from string theory perspective, I fix all of these branes, and then I'm looking at open strings beginning and ending, running between them. How do I know that there's a limit with, what's the limit where the gravity becomes? How do I know that?
Yeah, you want to look at sort of the dynamics that have these intersecting things. Let me maybe I will give an alternative perspective on this, which comes from field theory, and maybe we can discuss that. So the claim for now is that any of these webs engineers a field theory. What I have down here is a Curvature theory. Now this has 3 stacks of 2 D5s. So here's 2 D5s, there's 2 D5s, there's 2 D5s. So it's an SC2 cross SC2 cross SC2 Curvature gauge theory, and that is one way of arguing that Curvature gauge theories are actually okay, unlike the initial classification. And the example down here is actually interesting. That one doesn't have a gauge theory deformation at all. There's no way of pulling it open in a way that you would get a gauge theory description. But from the brain perspective, it seems fine. It's just out of what we can reach from Lagrange and methods.
Sorry, what did you say about quivers? Because this one is one of the ones that you are classifying.
Yeah.
So just you're pointing out that this is an example of a quiver.
This is an example which is not in the initial
class. As
classification.
a hint that maybe quivers in
Right.
general are fine.
Right. And the reason you can get around, so initially we were asking for one well-behaved effective field theory on the entire Coulomb branch. There can be different chambers of the Coulomb branch. In the different chambers, different gauge theory descriptions can be good descriptions.
What did you say about the last guy?
The last guy doesn't have a gauge theory description at all. This guy, in fact, doesn't have any relevant deformations. So there's no gauge theory, the gauge coupling is a relevant deformation. And this one doesn't have relevant deformations, so there's no gauge theory description.
What's known about it?
It's a rank 1 theory, it's a one-dimensional Coulomb branch, and you can study various things about it. Yeah, maybe not.
Who knows?
Good. So let's turn the picture upside down. So far we've engineered webs and said, okay, in all of those I can take a limit where I get a fixed point. What I want to do now is turn it upside down and say, well, the claim is then that every planar 5-plane junction of the type which I had on the previous slides realizes a 5-dimensional superconformal field theory on this intersection. And this, sure enough, is an infinite families of theories. They are characterized only by the charges that are involved here, subject to the condition that I have charge conservation at this vertex. So that's really the only constraint.
How is that supposed to? Is it clear that this is consistent with possible ways of filling in the vertex?
Yeah, basically.
Or is it just clear that there's only one way?
Yeah. The way you see inconsistencies, like if you go beyond NF equals 7 for the Sc2 theory, is you find intersections away from where you actually wanted to have this. So by starting with an OK intersection, you basically build it into the construction. Okay, very good. What I need to do is, these are lots of field theories, but they're not even enough to realize all of Seiberg's initial Sc2 theories. So I need to introduce one extra piece of data. And that is that I can generalize this construction slightly by introducing 7 branes in addition to the 5 branes. So what I want to look at here is an intersection. I'm drawing a bubble. This is supposed to be an intersection at a point. I'm just separating these branes slightly so I can draw them. And what I can do now is I can take a PQ5 brane and terminate it on a PQ7 brane. So these 7 branes basically fill out all space-time dimensions except for the plane which I'm working in here. So they appear as little dots, bubbles. And I can terminate each 5 brane on its 7 brane. And as long as each 5 brane gets its own 7 brane, that does not change the theory. So I put bubbles at the ends, but the theory is the same. What I can do now, though, is that I can do something like here, where I terminate multiple 5 branes on the same 7 brane, and that actually changes what field theories realized on this intersection. Well, there are additional constraints to how I can deform them, and this really affects the field theory. So the additional data then for a generic junction of 5 branes is that in addition to the 5 brane charges, I need to give you a partition for each group of like charged 5 branes into subgroups which end on the same 7 brane. So there's some combinatoric data associated with each of these legs of the intersection. That is the. And once you allow me to do that, I can actually realize all of Seiberg's Sc2 theories. So here's 0 flavors, 1 flavors, 2 flavors, 3, 4, 5, 6, and 7 flavors. You see that in the lower, in the E7, so the symmetry groups here are actually the global, if you wish, flavor symmetries of these theories, which are enhanced at the UV fixed point. And in the examples down here, 6 and 7 flavors, you see that 7 branes actually play a crucial role. So this is just to show a little bit how this works. I want to dwell a little bit more on these guys and generalize them a little bit.
Can you also just tell me how you can see the rank?
No, it's the way I've presented it here. It's not obvious. I can show you afterwards, though. It requires a little bit of acrobatics in drawing these web diagrams, but I will show you afterwards.
What happens to the ones that look like these but are not these? Like if I were to do different things with the blocks, it's either not allowed or I get some just not used.
Yeah, you may get different theories, or it may not be, depending what you have in mind for them.
I just mean like you chose here 3 different particular 7 brain configurations.
Because these realize the particular theories I want to show you. You can do different things. And let me tell you one example of what you can do. Is you can generalize it. So here we have a bunch of D5s, a bunch of NS5s, a bunch of 1,1s. And you can just allow for n of each of them. And then these theories are called 5D Tn theories. And those are the ones which are actually interesting because if you reduce them on an S1, so now we're doing compactifying from 5D to 4D, you get these class S theories, which I tried to advertise initially, which you can also get from compactifying a 6D theory on a Riemann surface with functions. So here we have a 5D perspective on this particular class of 4 dimensions. And the types of functions which you can have on the Riemann surface translate now to this combinatoric data to how I terminate the 5 branes on 7 branes. So this would be exactly your ballpark. The advantage of working in 5D is that the 5D theories can be deformed to Lagrangian gauge theories, which is harder to do in 6D. And this has actually been used to understand a little bit better these 4-dimensional classes.
Did you get all of them?
You get the regular functions from this construction. Good. So this was a little bit of a survey of 5-dimensional field theories. And what I want to do now is, well, in a way, maybe give an independent kind of evidence that these theories make sense, and tell you about holographic duals for these infinite classes of field theories. So what I want to say is, well, maybe you could take away from what I've been saying so far that the moduli spaces, mass deformations, various renormalization group flows can all be studied very efficiently using these brainwave constructions. But ultimately one wants more. One wants to have quantitative access, complete correlators, partition functions, all these nice things. And in the absence of a Lagrangian description, one way to do it is to use ADS-CFT. So we want holographic duals for all these 5-dimensional fields. And what the agenda for this is pretty clear. We have to repeat the usual story of ADS-CFT. So for our poster child, n equals 4 square Mills theory, you start from a brane realization on D3 branes. You construct the supergravity solution, which describes the near orbit close to these D3 branes. You find ADS 5 cos S5 in type 2D supergravity, and there you have your holographic description for n equals 4 square Mills. So what we have to do here now is to do the same thing for these 5-dimensional field theories engineered by brane junctions. That's a bit harder. The reason is that we don't just have a planar stack of D3 branes, we have these actually localized intersections of branes. They have less supersymmetry. In the 4D language, they are n equals 2, not n equals 4. And since we're dealing with localized intersection, you can imagine as you zoom in on an intersection point, you always have branes sticking out somewhere. You cannot get rid of them. So you're going to find some physical singularities in your solutions. And that just makes it a bit harder to construct the solutions. The Dps equations were first derived in studies a couple of years ago. And one of the things that we did in LA and before in Seattle was to actually solve the Dps equations with an ansatz that implements the physical features that we want to see of the brane junctions, and then construct actually regular solutions that describe the near horizon limit of these 5 brane junctions. So I want to highlight or give a little bit of an idea of how this works before moving on. And the idea is that we know what the 5D field theories have as a symmetry, so that dictates a little bit the ansatz for us. We clearly need an AES6 to implement 5-dimensional conformal symmetry. There's an R symmetry involved, which dictates that we need an S2. And that's basically it. So the geometry of these solutions is ADS6 and S2, and both of them are walked over space in the remaining 2 dimensions, which is a Riemann surface over which these 2 spaces. So you can make an ansatz. There are also fluxes which are allowed to form flux. The Jackson dilaton gets to depend non-trivially on the location of the Riemann surface. And if you look at the Dps equations, you find that there are nonlinear PDEs on this Riemann surface. And that is what you have to see. They're pretty messy, and I don't want to list them or discuss them. The point is, the solution actually has a nice structure. The solution works as follows. You get to choose any Riemann surface of your liking and a pair of locally holomorphic functions on it. And this pair of holomorphic functions parameterizes the general solution to the Dps equations.
Are this part of the metric on the Riemann surface?
Yeah.
These 2 functions?
Yes, these 2 functions enter the metric. They enter as the curvature radius of the AS6, of the S2.
Any assumption on the genus?
No.
Any genus
So
will
far.
accommodate 2 functions?
So far, yeah.
Okay.
So far. So this is a very general class of solutions.
So where's the, I think you said it in the words, but where is A plus minus?
A plus minus appears in the expression for the metric functions as in the harmonic fluxes. They're all complicated expressions in terms of A plus and A minus. Okay.
Well, what about the curvature of the Riemann surface? Is it negative?
It's not set to be constant.
Oh, it's not constant. Oh, okay.
Good. So this is sort of any choice, this is what I said in words, any choice of Riemann surface with two holomorphic functions gives you an ADS6 cos S2 solution in type 2B supergraph. But the point is, they're not generally well behaved. You don't want singularities which you didn't want in your solution, you want a consistent spacetime signature, and asking for these global regularity conditions constrains what you get to do, what you get to choose as your two holomorphic functions. And the picture that we found is that the case where we can construct globally regular solutions, which have a nice string theory interpretation, is when the Riemann surface is a disk, possibly with punctures. And these two holomorphic functions, it actually makes more sense to talk about the differentials. These differentials are allowed to have poles on the boundary of the Riemann surface. And at the punctures, they get to have SL2 homomorphic. This is sort of the general picture. For these kinds of choices, we find that there are globally regular ADS6 solutions. And the idea then is that at these poles is where you find 5 branes sticking out, and at the punctures is where you find 7 branes. So these are sort of singularities of the solutions, but they are physical in the sense that they have a string theory interpretation. And this gives us the solutions describing the near horizon limit of these fully localized 5 functions. So in more cartoon pictures, what you get to do is you get to pick your favorite 5-brane junction, characterized only by the charges. And as you zoom in onto the intersection point, you find sitting there on Riemann surface with a pair of holomorphic functions whose differentials have poles, the residues correspond to the 5-brane charges. You get a complicated solution which describes the near horizon limit precisely for this brane junction. The residues at these poles tell you what type of PQ it is. The monodromies will correspond to 7 branes.
Sorry, 7 branes are on the boundary of the disk or the
No,
interior?
they are in the interior.
And the interior has monodromies.
It can have. You don't need to, but you can have points of
I'm trying to understand how I see whether they're NS5s or P5s or
For example, so the differentials of A plus minus have a set of poles. They have residues. A real residue is an NS5 brane. Imaginary residue is a D5. 1 plus I times something is a 1 clone. So the 5 branes correspond to poles in the differentials. The charges correspond to residues. And the parameters are exactly the same on the supergravity side and on the string theory side. So that tells us that we're really understanding sort of what we're doing here, mapping between supergravity solutions and these brane intersections.
So this is a unique resolution.
Yes. After that took some while to figure out, but at the end of the day, this is sort of the gist. It's a one-to-one map between supergravity solutions and brane junction.
Actually, you can move around the poles and get some kind of moduli space, or they are really fixed?
They're fixed. They're fixed.
Okay, so that means that is what you're saying was unique. So
Yeah.
it's really, I mean, it gives you one solution.
One
you
solution.
can say,
You fix the 5 brane charges and you get one solution. What I should talk about then is usually when we want to write a CFT, there's some sort of large n limit involved. And the large n limit here corresponds to having all these P1, Q1, P2, Q2, and so forth, having all of these large. They should be homogeneously scaled up, and this is what corresponds to the large n limit, where classical supergravity is a good approximation to full string theory of this type. So that means generically we have each of these poles corresponds to a large group of like charged 5 branes. And to address the question for 7 branes, we can also construct solutions which have 7 branes in addition to it. And the puzzle which you may find is that, well, you have the 7 branes out here, and I told you the near intersection limit here is what's described by supergravity. You want to know how you see them at this intersection point. And the point is that you need to do a set of transformations on the 5 brane webs so that you can see them at the intersection. So you want to mass deform it, open it up to a web, do a set of Hanani-Witten transitions to move them into the intersection point, and then you collapse the web on the 7. So this is how the 7 branes become punctures in the interior of the disk. And the monodromies precisely correspond to these 7 branes. And then the claim of these ADS-CFT dualities is that Type IIB string theory on this particular warped ADS6 cross S2 cross sigma solution, which I tried to get a basic idea of, is holographically dual to the 5-dimensional superconformal field theory that's associated with this particular 5-point junction. And having these holographic duals, if you wish, is independent support that there's actually a field theory related, just by the basic principles of ADS. Okay, I think that's what I wanted to say about the holographic duals for these 5-dimensional field theories. And now to sort of the main part, I want to combine the string theory lingo and the supergravity solutions with field theory methods and derive some exact results for these theories and match them up between all these descriptions. So the idea is I tried to motivate these ADS-CFT dualities from a brain picture, which you may or may not believe. What we want at the end of the day is some independent field theory confirmation that we actually have holographic duals for some 5-dimensional conformal field theories, which somehow exist. And of course also new insights. At some point you want to learn something. But the first thing you would probably ask if someone hands you an ADS-CFT duality is, do the two sides, ADS description, field theory description, do they agree on the spectrum of gauge invariant operators? So there's some basic kinematic data which we do. And the challenge which we're facing here, of course, is again, we're dealing with some non-Lagrangian superconformal field theory. So whenever we want to match something between gauge theory and holography side, what we have to do is deform the non-Lagrangian CFT to gauge theory, compute the quantities of interest in the gauge theory, and then sort of flow back to the UV fixed point and to actually learn something about the data. And we did this for various operators which you could identify this way in field theory deformations and also in string theory. So this gives you a first idea that this somehow holds together and makes sense. But the operator spectrum is still somewhat kinematic data in that the operators we compare here are Dps operators. Their scaling dimension does not change along the flow. So they are not dynamical information in the sense that they will depend on the actual coupling strength. So what I would rather want to look at are partition functions. Something like which actually depends on the coupling and changes along the and that's what I want to spend a little bit of time on the last 10 minutes.
I think I didn't understand. So the brain picture usually is the answer for a lot of people who want to
Right.
understand about astronomical field theory. So you can do better? Is that, or you don't like the brain picture?
No, I like the brain picture, it's great. But for example, if you want to compute a partition function from it, it's not entirely obvious. If you want to calculate the correlator between operators, it's not entirely clear how to just read it off from the brain picture.
Sure.
You want something which is a bit more hands-on and allows you to do quantitative calculations. And I'm going to tell you a little bit how to do that. Good. So partition functions. What I want to look at here are sphere partition functions. And they're very interesting in odd dimensions. They are, for one thing, well-defined quantities. You can calculate scheme independent in a certain sense. And the free energy associated with the partition function, holographic, actually in 3 dimensions gives you a C function, so a function which decreases along the normalization group flows. In that sense, it gives you a way to measure the number of degrees of freedom to get a handle on that. So they are certainly very interesting quantities. In 5D, there's no proof for an F theorem, which is the theorem that tells you that the free energy is a C function. But it is conjectured to hold as well. So conjecturally, also in 5D, the 5-sphere partition function gives you a measure for the number of degrees of freedom. So that makes it very interesting. It is also interesting in that it really contains dynamical information. So this really, it depends on the coupling. It's different between weak coupling and strong coupling. So if you get these things to agree between string theory description and quantum field theory analysis, then that actually is something which you have a hard time arguing against. Okay, from a practical perspective, the partition functions are interesting in that you have a handle on computing them at strong coupling. even though their form is not fixed by supersymmetry. So that makes them very clear. And the idea for the remaining few slides is to first discuss these partition functions from holographic perspective and point out a few results, and then see how one can reproduce this from a field theory computation to give some ideas. Okay, so once you have a holographic dual for your theory of interest, the sphere partition function you can simply get by computing the on-shell action, in this case interactively. So it is technically a bit involved maybe, but conceptually very straightforward. And since I claim for any junction we know which solution to look at, I can immediately tell you what is the free energy for this Tn junction which I have. There's only one parameter here, that's n, the number of branes. So I'm looking here at maximal partitions where each 5 brane gets its own 7 brane. And the sphere partition function has a quartic scaling of this problem.
So I previously wrote such a list too.
Yeah.
So what is n?
Let me tell you what this is. So the claim is this is the partition function for the superconformal field theory engineered on this intersection point. But as in the examples before, there are relevant deformations for these field theories. And here I give you a gauge theory deformation for this particular intersection here. It's a linear quiver gauge theory. It has a lot of SUN gauge nodes, where the rank increases from 1 to n minus 2 instead of 1. And there are flavors, additional flavors at the ends after quiver. And between each pair of quiver nodes, you have bifundamentals connected. So from that, for example, you could calculate a recoupling partition. And what you would find is that it would have a cubic scaling, which is different from this enhanced quartic scaling which you find in strong coupling. So this is a fairly non-trivial claim, claiming that there is a particular scaling and a particular coefficient for the partition function, which is truly different from what you would find at recoupling. And that's all I want to say.
Expected number if you just counted the 3 and 5 dimensions.
Cubic. You get you have an adjoint for each gauge node, and then you have n of them. So roughly that's what it is. Second example which I want to look at is a slightly more slightly different intersection, just ND5 branes and NS5 branes. The gauge theory deformation is a similar quiver gauge theory, except for you get a bunch of SUN gauge nodes, m minus 1. And if you would do the exercise of counting the fields in the free field realization, you would find that it should scale as n squared, because you have SUN gauge nodes, and linearly with n, because each node just gives you an n squared. By contrast, what we find from the supergravity duals is that again, there is an enhancement of the scaling, n squared, m squared, as the scaling for the partition functions. And once again, there is an overall coefficient which involves a zeta of 3, but otherwise is fairly unreliable.
Can you say again how the theories are related? So the first one will flow to this fixed point in calculus. But then you have this F theory, right? And it's fine because in some sense it tells you that you lose degrees of freedom on an RG flow. So that's why what you are telling us, I mean, it's just a consistency check.
So far it's just a consistency check.
Okay.
Well, it is more than that. I mean, this is a particular target for a field theory computation. I'm giving you the benchmark, what will have to be reproduced in a field theory computation.
Exactly. But so at the moment nobody knows how to do so the field theory.
I will talk about it if time permits. Otherwise I may just give it.
This is the free energy at the fixed point.
Yes. The claim is this is a non-Lagrangian field theory at the fixed point which has this free energy.
And so the idea, the physical idea is that the strongly coupled theory, there are new degrees of freedom emerging, right? That's the interpretation. But do you know what these kinds of degrees of freedom are, or is there a way to understand?
There are two points to the answer in this. There are some degrees of freedom which are very clear. What you have as instantons in 4D become instanton particles in 5D, and those become massless at the fixed point. So that is an example of new degrees of freedom that pop into the whole consideration. Does that mean I can tell you what exactly is responsible for this particular enhancement? This is the
Can you
calculation.
repeat the example? What did you say?
Sorry?
Instantons and what?
In 4D, in 5D you have instanton particles.
Yeah.
Those are actually what is responsible for the symmetry enhancements in many cases. The point is there are new degrees of freedom which become light at a fixed point. They were in a sense already there in the gauge theory, but they become light.
And instant particles means they have a world line, right? So because I mean 4D with just one point in space and time, so here you have something like world line.
Good. So this is these are two specific examples. Once you have holographic dualities, you can make specific predictions. And that's what we're doing. There are also some general lessons which we can draw from the holographic perspective. And that is, you get to pick your favorite junction, and then the free energy, of course, depends non-trivially on all the charges that make up the intersection. But what I can say is if you do a homogeneous rescaling of all the external 5' charges, you get a quartic scaling of the partition. So in this case, you rescale all charges by the factor n, and you get an n to the 4. And of course, the Tn here, this n to the 4 was just a special case. And also in this case, you see you sum up the exponents, you get 4. So this is a very general feature for this particular class of 5 dimensions field theories. And if you are so inclined, you can compare this to other theories where similar concomitant enhancements happen. ADJM in 3D is into 3/2. The 6D theories are kind of cube. Here we have a particular class where we have a quartic scale. Sort of singles out a new class. And all the results, all the examples we looked at were consistent with the 5 dimension. Okay, so that sort of concludes the holographic discussion. And in the last few minutes, I want to give a basic idea of how one can reproduce this from a field theory computation, just giving the gist.
So, may I ask another thing? So just to understand, the technical complicated part was really to find the solution.
Yeah.
Because once you have the solution, you just plug it into the action, and then you get exactly the same value. So that's the simple part in some
That's
sense.
the simple part.
Finding the solution is the hard part.
The solution still involves polylogarithms and lots of lots of
even
polylogarithms.
evaluating
So
the
evaluating,
integral
yeah.
of the action is still.
It's not entirely, but conceptually it's straightforward. Once you have the solution. Conceptually, the challenging part is finding the solution. And at worst, you do it numerically. Okay, so now we want to switch gears a little bit and turn over to the field theory side. On the field theory side, again, we want to look at certain at gauge theory deformations, compute the partition function in the gauge theory, and extrapolate it to the strongly coupled fixed. And what I'm going to use here is a tool called Supersymmetric Globalization. The details I don't want to get into. What it does for you is it reduces the path integral which you use to compute the partition function to a matrix integral. And I'm giving you here the expression for the matrix integral for a generic 5-dimensional gauge theory. The details don't matter. The point is there is a finite dimensional integral which you have to evaluate. It is the Cartan algebra associated with the gauge group, it's G. It has a finite dimensional integral which you need to evaluate. And the point is, when the rank of the gauge group is large, you replace these eigenvalues on the I by an eigenvalue distribution, and you can evaluate even this matrix integral in a saddle point approximation, and that is exact in the large n limits which we typically think of for the rank of the gauge group. This is in principle straightforward. The challenge here is that for quivers this gets a little bit more complicated. You basically get one matrix integral for each gauge group. And that is basically the theories we were looking at. They were all quiver gauge theories. So for example, for the Tn and plus Nm theories, I gave you the quivers here. They all involve actually large numbers of nodes. So evaluating this matrix integral, even in the saddle point approximation, is non-trivial. But if you're interested more in the answer than in the way to get there, you can always do it numerically. And that was the first thing we did. I don't want to explain the plots here in detail because I want to talk very briefly about the analytic solution. But the point is, a numeric analysis confirms the scaling n to the 4 for the Tn theories, n squared, m squared for the plus theories, and it confirms the coefficients which we predicted from ADS-CFT at the terminal line. So this is really where you see that very non-trivial quantities agree between gauge theory perspective and the string theory perspective. But there must be something to this whole story, which I've been trying to set up and sell.
And this per null is just because you could make your n not much larger, right?
Right.
So when n goes to infinity, it should be exactly, but because you have to do this integrals for every called kind of factor in your Curvature gauge theory at some point you hit.
Yeah, that's exactly right. Okay, so as of fairly recently, I can also do these integrals analytically for you. And the idea to do them analytically is to first find a sharp characterization of the kind of Curvature theories that we're dealing with. So at a very broad level, we're always dealing with linear Curvature gauge theories. They have SUN gauge nodes. And the rank may change along the curve, SUN1 and 2 and so forth, up to some L. Each node may have a transimence term, indicated by a C here. And there may be additional fundamental hypermultiplets at each node, if you will. And the limit we're interested in is where this L parameterizing the number of curves here is very large. And this is what we have to treat analytically. And the way to do this is to switch from this kind of discrete set of data to something which is more adapted to the problem. So instead of having a parameter labeling the quiver node, which is discrete, I want to introduce a continuous parameter. So say T labels the nodes 1, 2, 3, 4, 5 up to L. I want to pass to a parameter Z, which is T divided by L, and that is effectively continuous at large. So the data characterizing the quiver gets replaced. The family of ranks, the n's, gets replaced by a continuous function of Z. And likewise for the flavors and the transimence term. In particular, the family of eigenvalue distributions, rho T of lambda, gets replaced by one function of two variables. The continuous label Z and this function. And if you feed this into this matrix integral, make the transition carefully, and mess around with it for quite some time, you find that these saddle point equations become some integral differential equations for this function of two parameters, and it can be converted to an electrostatics problem. So all I have to do is solve an electrostatics problem. In a cavity, where at the beginning and at the end of the quiver I have certain boundary conditions, in between fundamental flavors appear as point charges, and at some points where there are where the number of flavors at some points you can have conducting plates in the cavity. That happens whenever you have when the number of flavors is less than twice the number of colors. So this is just I'm giving you that as a fact. But the point is you have a cavity with some charges, conducting plates. Their position depends on the transimence terms. And this is not entirely trivial to solve, but fairly standard. So from this I can get a host of exact results. For the TN theories and the plus theories, I can now provide an exact match to the SCFT prescription. And if we look at the TN theory here with the non-maximal partition of these 5 branes, you get a very complicated function which was polylogs of degree 4 and 5. And this matches between supergravity and field theory.
And this is not just for large n, it's for all n.
This is for large n.
Oh, it's only for large n.
Yes. Right. In this case, you also get a quadratic scaling of the entire partition function, but it is really you're carving out a lot of theories. These theories, they have some complicated curve shapes, perhaps. They're parameterized by n, k, and j. And for each of these theories, I can give you what the partition function is, and it precisely matches to this. So this is beyond just matching scaling and coefficient. It's actually the function. Okay, and that is what I wanted to conclude with. One can do a similar discussion for the theories, but I don't think there's much of a point of it. And that brings me to wrapping it up. I hope I made a point that high-dimensional field theories are interesting, in many ways a rich source for new insights. What we have here is a new class of very many large n 5-dimensional superconformal field theories. They're characterized by an n to the 4 scaling of the degree 6 figure. They have holographic rules in term 2D, and they have relevant deformations that are given by long probabilities. The interplay between brain engineering, the SCFT, and field theory methods gave us very stringent tests on these points, and also new insights into the behavior of quantities like field. There is an interesting story of how these theories actually come. Some quantities in these theories come black hole matrices, but I don't want to open up now. As an outlook, with these tools established, the holographic dualities and the supersymmetric globalization under control, there are lots more things one can calculate, chart out, and map out. And the big point, of course, is to go down in dimensions and now use these new perspectives to study compactifications. Thank you.
So the end of the forest again, this is a, can I use this as an argument that these things don't have 6-dimensional progenitors? Because you know, you have, or is that too strong a statement? Because you're saying this, all the 62,0 guys, they're all n cubed.
Well, the thing is, if these guys have 60 parents, they would be 60 n equals 1,
Yeah.
they're not maximally.
So those are also classified as those.
Yeah.
So when you say new, I'm assuming that they're not those, right? So does that mean there's not under the 4 and the 1 and 0?
By new, I want to say that it is a new type of large n behavior. These theories are, yeah.
So-
I think it's consistent with that. I'm not sure if it's, I mean, yeah, I haven't thought about it. I think it's an interesting point. So the idea is, for example, the Type theory, the SU2 with NF up to 7, if you crank NF up 1 more and make it NF equals 8, then it flows to 60. So in a way, you can get a lot of the 5D theories by compactifying from 60 and then gapping out frames.
Right.
These theories here are intrinsically 5D, and indeed the scaling is steeper than for the 60 theories. At least for the data. It's consistent.
What do you mean when you say it flows to 60? You get an infinite number of like fields, which
Yeah.
in some sense open up a new dimension.
Yeah, you get no instanton states which complete basically KK towers. That is sort of the picture for maximally symmetric universe.
Was this like a consistent function? Stay in the fluid theory study? Because you're specifically able to delete entire KK towers.
I know that's a different theory. I mean, this is for maximally supersymmetric universe theory. The theories I've been talking about here are well, okay, depending on your choice of how you count supersymmetries, but it's 8 Poincarés, which is not 60.
You said something about constraints coming from the signature of space-time. What did you mean by that?
What I meant by that is that in the supergravity solutions, we have these curvature, this is the radius of the 86, this is the radius of the S2. If this guy became negative at some point, then you would get a weird signature. And that you better not have if you want to make sense of the solution in sort of some 10-dimensional string theory setting. And that gives you constraints on this pair of holomorphic functions that you are allowed to choose. It tells you that not any choice. And there's an interesting connection to electrostatics, the regularity conditions that I alluded to before.
I'd like to hear more about that. Anybody else have questions?